This is a recording of example number 6 from the 2-4A notes. I did this as a separate example. It's a little bit longer. There has been one like this on the test in the past. So I want to make sure that I do go over this particular problem so you can do the one that's on the worksheet. At what point is the tangent to this function horizontal? If we have a horizontal tangent line, that means a horizontal line has a slope of 0. If we could find the slope of this function at any x value, let's say call it a, if we could find out what the slope is at any value a, then we could figure out what that value has to be in order to produce a slope of 0. So let's start with our limit definition of slope at a point. Slope at a is the limit as h approaches 0 of f of a plus h minus f at a all over h. So I have to plug a plus h into this function. It goes in here and here when a plus h goes into the f machine. This is the limit as h approaches 0 of, and it's going to take a while. This numerator gets pretty long here. A plus h goes in here and here, so it's a plus h quantity squared plus 4 times a plus h minus 1. I like to bracket the a plus h part, especially as it gets more complex, and then bracket the f of a part, which is much easier. A squared plus 4a minus 1. It's all over h. Wow, that seems like a lot, but the algebra here should always be the same. As we simplify the numerator, every term that does not have an h must cancel. So we can factor out the greatest common factor of h and then reduce that factor of h in the denominator. So here it is. If we FOIL this, a squared, the outer and the inner, ah plus ah is 2ah plus h squared. If we distribute 4a plus 4h minus 1, distribute minus a squared minus 4a plus 1 over h. As you do these, and hopefully if you've listened to some of the videos or listened in class, because I say the same thing every time, every term that doesn't have an h must cancel in the numerator. If that doesn't happen, there's probably an issue. Maybe you distributed a negative sign incorrectly, or you plugged a plus h in incorrectly. But every term that doesn't have an h in the numerator is going to cancel. Here's a squared. Here's minus a squared. This doesn't have an h. Minus 4a. Oh, there's a plus 4a. See? I forgot to write down, nope, there it is. There's plus 1. There's minus 1. I did remember to write it down. Every term that doesn't have an h cancels because, look, I have 3 terms left. 1, 2, 3. They all have an h. So in the next step, you can factor this out front. But it's important that you do not cancel terms and factors in the same step. That is canceling terms. Now I'm going to factor out the h. I have a 2a plus h left in that term, plus 4 left in this term, all over h. Cancel, cancel. Now I have that h canceled from the denominator. And I'm left with 2a plus h plus 4. Once I cancel that h from the denominator, now I can take the limit by substituting in 0 for h. If I plug in 0 right here, I get 2a plus 0 plus 4 is 2a plus 4. 2a plus 4. Couple connections here we're going to make now. Number one, for those that were in honors pre-calculus last year and you worked with Mr. Hearn on the power rule for differentiation. Drop down the exponent, subtract 1 from the exponent. Think about this. If we go back up to the original problem here, if I take the derivative of this function using that rule, I get 2x plus 4. And I'm just plugging a in for that. Really, this process here produces the derivative of the function. That's what we're going to find out in chapter 3. This is a prelude to that. But right now, I want you to use this limit definition, because all of those properties or rules for differentiation that you talked about last year, at the end of last year when you did the JTBs, many of them come from this process. That's how we prove that those rules work in all instances, is through this limit definition of a derivative. But let's finish this question at hand on this particular problem that says, at what point is the tangent horizontal? If the tangent is horizontal, the slope equals 0. So I set this equal to 0. I can solve this by subtracting 4 to the other side and dividing both sides by 2. It's when a equals -2. That is the x-coordinate of this point of tangent C. If we plug this back into the original function, and I'll write it down here so I don't have to move everything up again, x squared plus 4x minus 1. If I plug this value in right here to get the y value, -2 squared is a positive 4. 4 times -2 is -8 minus 1. -4 minus 1 is -5. So the y-coordinate is -5. So the point of tangent C, where we have a horizontal tangent line, is the point -2, -5. Okay? Now, let's just make a connection here. If we have a horizontal tangent line for a parabolic function, doesn't it make sense that that would be at the vertex, right? This is really just the vertex. And you might say, well, I knew it was the vertex beforehand. It makes sense to me that the horizontal tangent line is at the vertex. Can't I just find the vertex by going -b over 2a or by completing the square on this? Not for this chapter. I could make these more complicated situations where finding this maximum or minimum point is not quite so easy. So we're dealing with functions that at the end you should be able to look at the answer and say, that makes sense, that it's going to occur at the vertice, or the vertex of this parabola. Okay? It's going to occur at the vertex. That's where we get a slope of 0 is at the vertex of a parabolic situation. And we just showed that we're definitely going to get a slope of 0 at the vertex through this process right here. Okay? So there's a lot of connections like that that we'll make first. And some of you have jumped ahead by knowing some of the rules for differentiation from last year, and that's okay. That's going to make that process better. But for now, we are using this limit definition process to find the slope at any value a.